And we're back to wrap up 14-3 where we're dealing with ideal gases. In this last podcast, we're going to show you how you can apply the ideal gas law to solve combined gas law problems. And then we're going to also talk about the difference between ideal gases and real gases. Okay, so example number 5 simply says a 5-liter air sample has a pressure of 107 kilopascals at a temperature of negative 50 degrees Celsius. If the temperature is raised to 102 degrees Celsius and the volume expands to 7.00 liters, what will the new pressure be? Alright, so once again, you start off with your equation, PV equals nRT. You take all of your changing variables, put it on one side of the equation. Put all your constants on the other side of the equation. In this case, the pressure is changing, the volume is changing, and the temperature is changing. And so what you're left with is, if I cross out the t's, PV over T equals NR before and after the change. So we can go with P1 V1 over T1 equals P2 V2 over T2. Alright, that's a mouthful to say, but that's how this thing actually works. So once again, if we rewrite this thing, we'll have P1 V1 over T1 equaling P2 V2 over T2. And now you simply have to plug in your numbers and solve for your remaining variable. Do we know the initial pressure? Well, the question says that it's originally at 107 kilopascals. So let's go ahead and put that in. I'm going to do it way up here. So you have 107 kilopascals. Do we know the original volume? Yes, we do. It's at 5 liters. Do we know the original temperature? The original temperature is at a negative 50 degrees Celsius. Of course, you do need to use the absolute temperature. So that's going to be 223 Kelvin. Now, do we know the final pressure? No, the question says, what will the new pressure be? So we'll just simply label that P2. The new volume is going to be 7.00 liters. And the new temperature, it was raised all the way to 102 degrees Celsius. So that means that it's being raised all the way up to 375 Kelvin. Of course, this right here is going to be 273 minus the 50 degrees Celsius to equal the 223 Kelvin, and then over here 273 plus 102 gets you the 375 Kelvin, just so you know. Now we just need to solve for P2, so we're going to multiply by 375 Kelvin over 7 liters. We're going to multiply by 375 Kelvin over 7 liters. The 7 liters divide out on that side. The 375 Kelvin divide out as well. And now P2 is simply going to equal this quantity, which is going to be 128 kilopascals. Okay? Alright, now, we've been dealing with ideal gases this entire time. Well, in reality, there are no ideal gases. The reason why is they do not behave exactly the way the kinetic molecular theory says that they do. The kinetic molecular theory says that the gas particles do not exert a force on one another, and they do not occupy a volume. Alright, well that's not true. Okay, the reason they do not perfectly conform is that they do not conform, to the kinetic molecular theory. And once again, the two reasons why they don't conform to the kinetic molecular theory is simply that particles do, in fact, exert a force on each other. They slow each other down. And particles do, in fact, occupy volume. And so, though we're not going to test you on this, some of you will be taking a look at this in AP chemistry. Rather than saying PV equals nRT, what you have to do is you have to correct the pressure and the volume. What ends up happening is the pressure, what you actually observe, is less than what you would expect because they do slow down the particles as they approach the container wall. So because they slow each other down, the pressure is actually slightly less than what it should be, what you calculate. So in order to correct for that, we take the observed pressure and we add a correction factor. Now again, you don't have to memorize this. This is only for those who will eventually see this again. But this is a correction factor to pressure. If you want to have the pressure match PV equals nRT, you have to add in the pressure that you expected to get, but again, it was slowed down. Same thing with the volume. The volume is going to be corrected as well because the actual volume is slightly less than what you would expect or what you would actually calculate. So really, here's the new pressure, here's the new volume, and that is going to equal nRT. This is actually called the Van Hoff equation, or I'm sorry, not Van Hoff, the van der Waals equation. And for some of you, we'll be talking more about that in the AP class or in a future chemistry class, something you might take at the college level. Okay? All right, that concludes 14-3.